What we want to do now is a test that usually determines the flexural strength of concrete or fiber reinforced concrete. And for that, we are taking a beam, we are supporting it as a simply supported beam. That means it is free to rotate at the supports, and we are applying a point load at midspan of that beam. What is taking that tension on the bottom if there's no reinforcement? Is there anything that can take the tension on the bottom? There's nothing there, right? So that force couple between compression and tension is not present, right? So if we don't have a tensile force on the bottom, we can have an astronomical compressive strength on the top. If there's no tension to equilibrate the compression, then we have failure of the beam. Yeah? So now what we're trying to do is we're trying to introduce something into that concrete that can handle the tension. What is normally responsible for tension in concrete? Rebar, right? So in this case, what we're trying to do is we want to incorporate the tensile element in the concrete mix itself. So we are adding these steel fibers. They are typically on the order of 50 millimeters long, below a millimeter in diameter, and they have different shapes, different kind of cross section. Some are plain, they are just straight fibers. Some have hooks at the end. Some others are twisted. Yeah? All to make sure that the steel fiber, why would we have a hook at the end? Why not just have a plain fiber? What is better with a hook at the end? The anchor, right? So we want to make sure that these fibers really get anchored into the concrete. Because if they are plain and smooth, it's very easy to pull them out, right? So in order to investigate the effectiveness of different types of fibers, we are typically performing a test like that. What we're doing now is we're casting the fiber reinforced concrete into these beam shapes. They are 600 millimeters long, 150 by 150 in cross section, and then we support them in a machine like that. The span is 450, 500 millimeters in this particular standard. This is a European norm, EN. I can give you one copy, you can make a copy for yourself, just to read up on it. So the span length in the machine is 500 millimeters, and the load, the center load, is applied at 250 millimeters away from the support. And then in addition to the beam that I just described, we have a notch on the bottom. Why would we do that? Why would we cut a little slot in the middle of that beam?
So you know where it cracks?
Okay, we want to make sure that we know where the crack occurs. If we don't have that notch, the crack could occur in this type of setup somewhere around the middle, but we don't know exactly where. Okay? You can see on the bottom of this beam we have a little device. It's a little clip gauge, as we call it. That clip gauge is measuring the opening of that notch. Yeah? So now that we have the notch, we know exactly where the crack will happen, and we can monitor the crack opening as we apply the load at midspan of that beam. Okay? So what we will get out of this is, of course, a load versus deflection curve. Right? The machine can measure the load. It can also measure the deflection. In addition, we will also get the information on how wide is the crack as we apply the load. Okay? So these two very important aspects, load deflection and load crack opening, is what we want to get out of this test. Later on, and you can read that in this standard here, we are converting the load into a equivalent flexural stress. Okay, we have a formula which is very similar to Navier's formula. M is equal to, cut that, Holger, sigma is equal to my over I. Yeah? So a similar expression is explained in here, and you can get a flexural strength for this type of concrete. Yeah? Any idea what a typical flexural strength of concrete is if it's unreinforced? What do you think? What's a typical compressive strength of concrete? 30 megapascal is a good compressive strength. What is the tensile strength of concrete? Around 1/10. 10%, exactly right. So about 3 megapascal we would expect in direct tension. Yeah? The flexural strength of an unreinforced concrete beam is also 3 megapascal. Now that we have fibers, you will see that after the crack has formed, that the fibers will contribute to the loading capacity. So we will get, depending on the composition, we will get a slowly or a gradually dropping response. The load goes down as the crack width goes bigger, or we will get a hardening response. What would that depend on? When would we get a gradually declining load, and when would we get a gradually increasing load? What do you think? Let's say I ask you to make a fiber reinforced concrete that goes stronger after the crack has formed. What would you do? You are making that concrete. What would you try to do if I say you have to deliver that? What would you do?
Put more fibers in it.
Put more fibers. Very good. But that's the obvious thing to do, right? So as the fiber amount goes up, right, the fiber volume fraction, as we say, then it is more likely that you get a hardening response after cracking. And we will see on the display what this particular material will do, if it goes up or goes down after the crack has formed. Okay? The standard that we are following with this test is called EN, European Norm 14651. This particular version right here, I can pass that around. You can have a look. And today we have Amela and Andrea who will help us perform this test. They are doing this for their master project. They have tested many beams and they will test even more in the future. So today they will demonstrate to us how this test is being performed. Okay? Any questions? How wide do you think we can make that crack before we have zero load? Let's say the fiber is 50 millimeters long. How wide would we have to open the crack for the load to drop down to zero? Have a look. We have zero crack opening at first, and there's a fiber bridging that crack. And we open this crack. How wide can we make it before the fibers cannot carry any load anymore? The fiber is 50 millimeters long. Let's say the crack is 100 millimeters open. Any chance there's any fiber left? No. Let's say 50 millimeters. Also no, because the fibers are only 50 long. Right? How about 25? What do you think? What does that fiber do as the crack opens? It slides out. How much of that fiber can slide out? 25 millimeters, right? At least in theory, right? So the fiber typically hangs on with the larger embedment length, right? So let's say the fiber is whatever, 15 and 35. The portion that is embedded 35 stays solid, and the one that is 15 pulls out, right? So by chance, you might have some fibers that are positioned so that one embedment length is 25, the other one also 25. So this one would pull out 25 millimeters before the crack cannot be bridged by this fiber anymore, okay? This test we will run up to crack widths of about 4 millimeters, okay? Why would we limit ourselves to something that is much below the theoretical 25? Let's say we had fiber reinforced concrete in these beams and you have a crack opening of 4 millimeters. Would you still say, well, that's okay, we can put more? No, right? So the crack width that we feel comfortable with, right, if we see something, is limited to 3.5 or 4 millimeters. What would go along with a large crack width? What would you see in that beam? Of course, you might be able to see that there's a big crack, but what else would you see along with that? Deformations, right? That beam would deflect a lot if the crack width is 4 millimeters, for example. And you will see that here. Here we are trying to limit ourselves to only one crack. Now we want to measure what is the response of the material in terms of crack opening as we apply a load. If we had several cracks, we would not know if this crack that we're measuring is characterizing the material well or not. Yeah? So we are trying to limit it to one crack. That's why we have that notch. Okay? All right, any questions? Okay. So let's walk around. You can, if you want, you can take a look here. We will want to position ourselves so that everybody can see what's going on in the specimen. No, that's too detailed. Okay, so the machine, of course, can measure the load, and the machine can tell us where this part is positioned. Okay, this is the machine displacement. At the moment, we say this position here is 0. And as we are moving down, this position goes up from 0 to 1 millimeter to 2, 3, 4, and so on. Yeah? So the machine tells us the load and the displacement, the movement of this point. Okay? We also have this additional gauge down here which will tell us the crack opening. So every tenth of a second we are reading. So 10 times per second we are reading these three quantities: load, machine displacement, and crack opening. And we get an Excel file afterwards that will tell us the time, of course, when was that measurement taken, the load, the displacement, and the crack opening. On the screen here, you see exactly that. You see the displacement in millimeters. Yeah, so at least at the moment it says 52 millimeters. That means that this piston or this loading point here is at a position 52 millimeters. As we move down, it goes up or down? It goes up.
Down, sorry.
It goes, so 52 goes to 51, 50, and so on. Yeah? It will tell us the load in kilonewtons, and it will tell us the opening of that little gauge on the bottom. Okay? The way that the machine does that, it gives us voltage. It does not say anything about kilonewtons right away. It tells us volts, between 0 and 10 volts. And this range between 0 and 10 volts is equivalent to some displacement, equivalent to some load, and equivalent to some crack opening. So every time when we want to use a new device in a test, we have to calibrate it. We have to say, if the device tells us a change of 1 volt, what does that correspond to in terms of crack opening? Or what does that correspond to in terms of load? Yeah? So every time that you would normally run a test like that, you would have to do this calibration. Of course, for this machine, it has been done before. Right? Load and displacement, they are standard outputs. But every time we use a new device like that, we will have to take a little reference crack, open that a millimeter, and ask, well, how many volts was that now? And we make some sort of correlation between the voltage output and the actual displacement or the load that we want to measure. Okay? In this standard here, there is an explanation of how fast you want to run that test. This is also standardized. So the configuration is standardized, like the span and where to apply the load, how to cut the notch, but also we have information or a guideline on how fast to run that test. We don't want to run it too fast because then we might not be able to capture the important details that we want to see. Okay? So at the in the beginning, especially before the first crack occurs right here, we will run the test very, very slow. How slow?
0.05 millimeters per minute.
So 50 microns, half the size of your hair per minute. Yeah? Extremely slow, because this beam is quite stiff, right? So it will not deflect a lot before the crack opens. The crack occurs very, very early. You might not even be able to see a deflection when that crack occurs. So the first sign of a deformation that you will recognize if you come very close is you will see a crack protruding upwards from the notch. Okay? There's also a very important detail in these supports, and this is actually a matter of discussion in the research community. How do we detail these supports? Sometimes we have stiff supports that doesn't allow the beam to expand horizontally. Others, like what we have right here, are allowing the beam to expand horizontally. Let's just imagine for a second that we keep the beam fixed right here and fixed right there, like a bridge in a way, and we apply a load. You think that load is higher or lower than if we were to allow movement? We keep it there and we apply a load. What would happen inside this beam here if we have sort of an abutment on both ends? More load, right? Because this point is trying to deflect the beam, and the deflection is constrained because of these two abutments on the ends, right? So some test setups are configured in such a way that the ends are not allowed to move, right? They are allowed to rotate, but not allowed to move laterally. So those tests typically give us a much higher flexural strength than what we would see if we were to allow. You can see here, right? We are allowing the movement horizontally. So this will actually give us the true response of the material without this misleading effect of the abutments. Okay? Otherwise, the machine has a capacity of 250 kilonewtons, corresponding to about 25 tons. What do you think? How much can this beam handle? You must have some idea. 1 kilonewton. Okay, that's pretty conservative, right? That's a little bit less than me standing on it. Okay, so it can handle that. So it's above 1. What do you think is the upper limit? What would you feel absolutely uncomfortable with? 1 kilonewton is 100 kilograms, right? So let's say 10 is a ton. A car resting on this. Still okay or not? Let's say 10 or so, right? 10, 20, 30, something like that, depending on the material. Let's see. Yeah? So of course, whenever you design a test like that, you want to make sure that the capacity of the machine is according to what you are expecting in terms of load. Right? You would not want to take a much smaller machine like this one over there and run a test like that. Yeah? It might actually be able to apply the load, but since the column is much, or the machine is much smaller like that one over there, it would also have very large internal deflections, right? As we apply compression downwards here, what does this post and that post, what do they see? Compression or tension? This one pushes down. What happens here? It goes into tension, right? So if you have a massive machine like this one over there, right? This one is very stiff, so it would have very small internal deformations as the test is going on. If you have something much smaller, the machine would actually expand a lot. Yeah? And then upon cracking, it would very quickly apply very large deformations. Okay? So you also want to consider the stiffness of the machine as you are running a test like that. Okay, so on the screen, we will see on the vertical axis the load, and on the horizontal axis the opening of the crack.
Yeah.
Right? Okay, so we see load versus crack opening. You will get, whenever you will run your test, you will get a file like this, and then you can evaluate this file. What you will get is load versus crack opening. What we want to have is a flexural strength, and how to convert the load into a flexural strength is explained in the standard, so you can follow this. Yeah? Okay, so let's give it a go. So you can come closer if you want to see what that crack looks like, and you can compare load deformation versus crack width.
If you want to
see
show
this
them,
kind of graphics, you have
Not
to do
yet,
it.
not yet, later. So right now, of course, you see a big mess here on the screen. Right? This is because the machine is very sensitive, right? And there's a lot of vibration going on. So if the load and the displacements are quite small, it will give you a big messy plot like that because it's jumping back and forth. Once the load is actually applied on the beam, once we have pushed it that far down, then you will see a nice trend. Okay? You can read here how the load is changing, and you can read here how the position of the load point is changing, and you can see here how the opening of the crack is changing. So at the moment, we have a displacement of that gauge of 6.522 millimeters. As we are applying the load, let's check what happens to that crack opening. Okay? At the moment, there's of course no crack present, it's just a notch. So as the load goes up, right, we are now at 6 kilonewtons, the crack opening has increased by 10 microns, 10 micrometers, a hundredth of a millimeter. Yeah, very small. But now, once we reach the cracking load of this specimen, you will see that the crack opening jumps up very quickly. Huh? When does a crack usually?
like 20,
20. Okay.
15, 20. It depends.
So in the beginning, right, we didn't see much of an effect as we have moved the piston down. Now that the load has engaged with the specimen, the load goes up very quickly. Right. So you can see here we're now at 12 kilonewtons, 1.2 tons. The load deformation relationship now goes nonlinear, right? It used to be a straight line right here because everything was elastic. Now there is probably a small crack starting to propagate at the notch. And once this line here reaches a zero slope, typically we get a crack. So we can observe that here. So it's no more linear right now. Okay, so now we have a crack. And if you want to come closely, you can now see what that crack looks like.
Oh yeah, yeah. It's very small. Very small. Yeah.
So we were at about 23 kilonewtons, 2.3 tons. we applied to the beam before cracking started to occur. Okay, so right now the crack is at about 2/3 of the height of the beam. Yeah. So above the tip of the crack we have compression, below we have tension. Yeah. So you can see now that unfortunately our
Yes.
device was lost. Right? So now of course all we are left with is the displacement of the machine and the load. There is, however, a relationship between displacement, that is deflection of the beam, and the opening of the notch. Yeah, you can also read that in the norm, how we can theoretically relate deflection to notch opening. Okay? But typically, we would want to maintain this measurement up to a crack opening of 3.5 millimeters. The way that the norm tells us to evaluate this material is to find out what is the flexural strength at a crack or a notch opening of 0.5 millimeters and at 3.5 millimeters. So this is how we evaluate these materials. Okay, so now instead of the crack opening, we will run the test up to a deflection of about 4 millimeters. So you can see that the crack continues to open as the deflection starts to, or continues to increase, and the load is dropping continuously. Yeah? So this material here would have a softening after we have reached the cracking load. So it starts to lose strength as the crack continues to open. If you had more fibers, it would potentially gain strength as the crack is starting to open. You can see now that our idea of having one crack only does not really apply, right? There are several cracks in parallel that are forming in this material. Yeah? But since we had the notch introduced and we are measuring the opening of that notch, right, then we would all lump this together, these different cracks, into measurement of one crack opening through this notch. Okay? Any questions? All right. So when you guys have your appointment with this test RF, then you come down here and Andrea and Amela will wait here for you and they will run this test with you. Do not do this on your own. It's very difficult to position the beam up there and to run the test. So I would prefer that you just assist them with the specimen, and they can explain to you in detail what they are doing at that point. All you have to do is take notes, take pictures, and of course analyze that file afterwards, once you get it. So your role would be an evaluation or an analysis of that test, not to run the test by yourself for safety reasons. Okay? So there's not much more that will happen now, except that the crack will continue to open. Yeah? So unless there are any questions, we can now move downstairs to the basement and look at the compression test.